Welcome to this lecture on energy conversion and storage techniques. So today we are going into the third unit. We'll be discussing about energy storage systems, and specifically about battery storage, battery energy storage, the different types of battery energy storage systems available, the construction and the operation of different types of systems. So we have already had a brief idea on what is battery energy storage in your first unit. And we have briefly had a look on the different types of batteries as well in your first unit. Here we'll be dwelling much more deep into the construction and the types which are being used currently, as well as their operation. And then we are going into in specific about a few of the thermal energy storage systems and your mechanical energy storage systems. So under thermal energy storage systems, we are well aware of the two main categories, your sensible heat storage and your latent heat storage. So we are going to talk about sensible heat storage systems and phase change materials. Then under mechanical energy storage systems, we are going to be seeing about in specific about flywheel energy storage and compressed air energy storage. So a brief idea of all these things have been discussed in your previous units as well. So in this lecture, we'll be starting off with the battery energy storage in this lecture. So we all know that battery energy storage system is a critical technology which seems to rapidly shape the future of our energy systems. So as you can see in this slide, battery energy storage falls under the broad category of electrochemical energy storage systems. So think of it as a family of technologies that use chemical reactions to store and release electricity. So within this family of technologies, batteries are very key players. So these systems are crucial for our modern energy management. So as our world becomes increasingly reliant on electricity, managing its flow and availability, efficiency is very important. Batteries allow us to store energy during periods of low demand and release it during uh, demand times. So this helps basically in stabilizing the grid and optimizing the use of our energy infrastructure. Crucially, if you see, it helps in enabling the integration of your renewable energy sources like solar and wind. So when you have a system which produces energy at seasonal times, you need systems to store these energies. So then battery energy storage is one of the key player. So when you look at this slide, when you see the publication works within the last 12 years, you can see that the number of publications which directly represents the number of research have increased almost 60-fold in term for your lithium ion batteries and also your battery management systems. So we know very well about battery management systems when we use array of batteries and the heat management, the voltage management, storage management all comes into picture. So first we are going to be seeing about something called as primary batteries. So battery energy storage systems are classified into two main categories. One is primary and another one is secondary. So these primary batteries are a foundational technology in the world of portable power. So as highlighted on this slide, the primary aqueous batteries have existed for over 150 years. So these non-rechargeable batteries played a pivotal role in the early days of electrification and they continue to be relevant in specific applications. So these first batteries, which are known as zinc carbon batteries, evolved into two main types. One is a Lackland cell and other one is a zinc chloride system. So these early designs, they address the need for more reliable and less corrosive power sources. However, in modern times, the usage in countries like the United States and Europe is in a downward trend. So this decline is largely attributed to the rise of more advanced battery technologies and the increased energy demands of modern electronic devices. Despite these reasons, due to the low cost, wide availability, and acceptable performance for a large number of applications, it is still used in emerging countries. So these are used in regions where access to recharging infrastructure is limited or where cost is a primary concern. So here in these places, the zinc carbon batteries and alkaline cells, they remain a practical power solution. So you may be wondering what exactly are these primary batteries? They're nothing other than your daily use everyday batteries or your Duracell batteries, the non-rechargeable one batteries. So these aqueous primary cells, they use a metal anode. So zinc has historically been the most popular anode material due to its favorable electrochemical properties, compatibility with aqueous electrolytes, and low cost. They also utilize a manganese dioxide cathode and a chloride salt aqueous solution electrolyte of nearly neutral pH. To enhance the performance of these cells, you have a carbon, that is acetylene black, which is mixed with manganese dioxide to improve conductivity and retain electrolyte solution. This ensures that better electron flow and maintains the necessary ionic conductivity within the cathode. So as the cell is discharged, the metal foil is oxidized and the manganese dioxide is reduced. So these electrons which are released during the oxidation of the metal anode flow through an external circuit to the cathode. So this concept we have already seen in our previous units. So that outer passing electrodes, they participate in the reduction of manganese dioxide. So a simplified reaction is given below. Zinc plus 2MnO2 gives ZnO dot Mn2O3. So when countries face increasing competition from these rechargeable technologies, especially in our developed nations, these primary zinc carbon batteries, they continue to serve a significant role, mainly due to their affordability and accessibility, demonstrating their impact of early electrochemical innovations. So the annual growth of these zinc carbon batteries from 1997 for almost 15 years was estimated at 5% per year. So this demonstrated a sustained demand for this mature battery technology for a significant time. So the primary drivers behind this global demand were the markets in Asia and Eastern Europe. So in these regions, the low cost of the inexpensive zinc carbon battery system made it a practically attractive option for a wide range of applications. However, this landscape began to shift due to several factors. So one of the main factors was the use of heavy drain toys, lighting, and communication devices, which entered into the consumer market, which caused a decline in the zinc carbon cells and the growth of zinc alkaline cells. So the superior performance characteristics of these alkaline batteries made them a preferred choice for these more demanding applications. So when you go to a general market, you very commonly see these zinc carbon batteries as well as these zinc alkaline batteries also. So they come in the same shape. So the improved alkaline cells and expanded use of rechargeable cells will continue to negatively impact the sales of zinc carbon batteries. However, if you see the convenience and long-term cost savings of rechargeable batteries coupled with the enhanced performance of alkaline batteries, they present a strong competition to the traditional zinc carbon cell in many markets. Okay, so next we are going to be seeing in specific about your Lagrange cell or Lagrange battery. So was a truly significant innovation in the history of your primary batteries. So the Lagrange batteries was invented by Georges Lionel Lagrange in 1866. So it's more than 150 years. So he was a French telegraph engineer who created a design that addressed the limitations of your early primary cells. So it was the first aqueous primary cell to use a single low corrosive, that is a neutral pH salt solution. So prior to Lagrange's work, the primary batteries often employed corrosive solutions such as ammonium chloride or mineral acid solutions. Lagrange innovation, it offered a more stable and user-friendly power source. So this battery designed by Lagrange provided a more reliable power source for telegraph offices and railroad signaling, which were important offices in those days. So in these crucial applications, a dependable and consistent source of electricity was essential, mainly for communication and for safety. So the Lagrange cell was the most widely used primary battery in the 19th century until the rise of your modern alkaline batteries. So for almost a century, it was the dominant force in portable power. So it powered a vast array of devices after being superseded by your alkaline batteries due to their superior performance characteristics. So a key aspect of its history is the evolution from your wet cell to a dry cell. So the original Lagrange cell actually used a liquid electrolyte. So this development of the dry cell is actually credited to a person called Carl Gassner. So he made these batteries more portable, unbreakable, and spill-proof, which significantly expanded its range of applications. So coming to the design of these batteries, so first design which we see is your cylindrical design. So which is a dominant form of this primary cell. So this is the exact cross-sectional view of your day-to-day use everyday battery. So as this slide highlights, the zinc can serves a dual purpose. It acts as both the cell container and the negative electrode, that is the anode. So this indigenous design actually simplified the construction and effectively utilized the zinc material. So inside this zinc can, you will find a bobbin at the heart of the cell. So this bobbin is a compressed mixture of manganese dioxide, acetylene black, and electrolyte, which typically is ammonium chloride or zinc chloride solution. So the acetylene black plays a crucial role in improving the low electrical conductivity of manganese dioxide and also helps in retaining the electrolyte solution. So in some time or other, we would have opened these batteries and seen, we would have seen the bobbin, which is basically a carbon rod. So this carbon rod is inserted into the center of this bobbin. This rod, which is often wax impregnated, acts as the current collector for the positive electrode, which is the cathode. And this also provides the structural support while allowing gases to escape. So the separating material between the zinc anode and from the manganese dioxide cathode is called as the separator. So the first early Lagrange batteries, they commonly used a cereal grain paste, so wet with the electrolyte as a separator. So later designs saw the introduction of this craft paper impregnated with the starch or polymer coatings. You can see that thing in your figure. So this evolution to a paper-based separators allowed for a thinner barrier low internal resistance within the cell, and an increased volume availability for the active electrode materials. So finally, all these materials have to be sealed to prevent leakage. So early Reclan cells, they typically used thermoplastic material such as your asphalt pitch and waxes for sealing. Uh, Although they are inexpensive, these seals were often found to be less reliable, especially when it is at an elevated temperature or under excessive gas generation. So later, these Lechland cells used almost zinc chloride cells, which adopted injection molded plastic seals. So you can see in this picture also you have the plastic seals. So these advanced seals incorporated your positive venting mechanisms and allowed for greater reliability in preventing leakages and controlling the gas release without significant moisture loss. So next one is your flat cell design. So this design offered very distinct advantages, particularly in terms of efficient packaging. So the key element of this flat cell design is the duplex bipolar electrode. So this is constructed by coating or laminating a conductive carbon polymer directly onto one side of the zinc plate. So this layer serves a critical dual function. It acts as a negative electrode for one cell in a multi-cell battery and simultaneously as a positive current collector for the adjacent cell in the stack. So unlike the cylindrical design which we just discussed, the flat cell design eliminates the bobbin of manganese dioxide and the central carbon rod. Instead, these flat cells are assembled in a flat stack construction. So this layering of cells, one on top of the other, allows for a more compact arrangement within a battery. So you can see the figure where it is given in stacks. So each stack has been shown in the enlarged image. You have a plastic envelope in which you have the cathode mix, the separator, and the anode. So this flat stack configuration leads for more efficient packaging as it minimizes the um, space which is wasted within the battery casing. So this efficient use of the volume directly reflects in the higher volumetric energy density than your conventional cylindrical assemblies. So this flat cell design has a significant advantage in delivering more energy for a given battery size. So we know very well the batteries of this kind come with a 9 volt rating, whereas your cylindrical generally come with 1.5 volt rating. So coming to the advantages. So both Lechlange and zinc chloride batteries, they share several key advantages. First and foremost advantage is that they offer a low cell cost and a low cost per kilowatt hour, so making them economically attractive, especially in price sensitive markets such as your developing countries and underdeveloped countries. And they are available in a wide variety of shapes, sizes, voltages, and capacities, which provides a flexibility for different device requirements. So when you come to your normal cylindrical battery, you have AA category, AAA category, and when you go to your olden shops, you will see many other different sizes. So they also benefit from wide distribution and availability across the globe, and they have a long tradition of reliability, so built upon over a century of use and refinement. The refrigerated shelf life is good, which can extend its usability if stored properly. Specifically, the zinc chloride variant of the battery offers good shock resistance, so it's making it suitable for more demanding physical environments. Although they have a lot of advantages, they still have a few disadvantages, or you can say limitations. So both these batteries, they exhibit low energy density, which means that they provide less energy for their size and weight compared to your more advanced batteries. In those times when they were manufactured, they had the highest energy density, but with the production of a secondary batteries and alkaline batteries, comparatively they provide less energy. And they suffer from poor low temperature and high current drain performance, which limits the effectiveness in devices with requiring high power or in cold environments. So they also have a poor leakage resistance under abusive conditions, and at room temperature they have a comparatively poor shelf life. Another important characteristic is that their voltage falls steadily with discharge. So this can affect the performance of a few electronic devices which requires a stable output voltage. So despite these advantages, you see zinc carbon batteries, they continue to find use in multiple applications. So some of the common applications are given here. So first application is in your flashlights and portable radios. And the second one is they found in toys, and they are used in novelties and instruments where a low cost power source is suitable. And they find growing use in emerging countries for moderate and light drain applications which are driven by their affordability. So from this we can to a certain extent conclude that Electlanch and zinc chloride batteries, they remain relevant even after 150 years of production due to their low cost and widespread availability, particularly in specific markets and applications. So the applications are mentioned here. However, you see that the performance limitations, specifically you can say about their energy density and high power demands, they are not applicable. So this has led to the dominance of your alkaline and rechargeable batteries, which are there in consumer electronic markets. Okay. So with this, we are done with your primary batteries, which are generally non-rechargeable batteries. So from my upcoming lecture, we'll be seeing about secondary batteries, which are also known as rechargeable batteries or storage batteries. So we will discuss about them in your next lecture. Thank you.